We conclude this section with two examples. First one is an example where deers are reproducing themselves. So in 2006, you've got 80 deers that were introduced into a wildlife refugee. By 2012, the population had grown to 180 deers. You use an exponential model to represent the population N of t over time. And how many deers will there be in 2021? So first of all, we need to construct our model. Here you see we're told that it's an exponential model. We cannot deduce this from the first sentence. So from the first sentence, I have 80 deers in 2006. All I know is, let's say 2006 corresponds to times 0. Okay, so I know that there are 80 deers here. And in 2012, which is 6 years after, there's 180 deers. So a lot of curves that could actually fit through this. So I could use a linear model if I wouldn't be told what to use. I could use a quadratic model. Who knows? Like fit a quadratic through those 2 points. But here we're going to try to fit an exponential model like this. Okay. It's usually a good model to look at when you have population growth, by the way. So here we know that N of t, if it's an exponential model, so we know N of t is going to be a times b to the t. This is what an exponential function is like. So we don't know what a and b are. So the idea is to try to recover those values using the 2 points given. Okay, so now let me throw in the first point. 0, 80 means that n is 80 when t is 0. And for the other one, I've got n is 180 when t is 6. Okay, so from this, can I deduce something? Well, b to the 0 is just a, so I can easily deduce that a is 80 from this, okay, which I can actually tell because my y-intercept for my exponential model is corresponds to a, so I knew that already in some way looking at the graph. And then 180 is a times b to the 6, so replacing a by 80 gives me an equation for only one variable b. So I divide 180 by 80. That's b to the 6. And finally b is going to be, so to remove the 6, I need to multiply everything on both sides by 1/6. Well, not multiply, I need to raise it on both sides by 1/6. So b to the 6 to the 1/6, that's going to be b to the 1, not 6 to the 1, b to the 1. Okay, so b is going to be 180 over 80. So this is 18 over 8, and this is 9/4. 9/4 to the 1/6. Now I can just punch that into my calculator. That's going to give me 1.447 approximately. You see the approximate sign here. So I've got that n of t, hence is like therefore in math. It's a word that's used a lot in math. A is 80, b is 1.447 to the power t. That's my model. And remember that they're asking me to use my model to deduce how many deers there will be in 2021. That's 15 years from now. So n of 15 is 80, 1.447 to the 15. If you calculate this, you get approximately 607 deers. Okay, so what's going on here? You've got your population that goes like that. It starts at 80 and then just increases real fast. So Okay, those are the two things we wanted to find. Next example is simpler in the sense that it's just a math question. There's not, in that sense that there's no word problem here. Find an exponential function passing through two given points. So that's kind of like what we did before, because we had like 2 points, like for the deer problem that were given to us. The difference here is that I don't have that one of these 2 points is the y-intercept of the curve, so I'm not going to get a straight away. So I'm going to call f of x a b to the x. Now you see, and so let this be my function, and f of minus 2 is 6. So that's a b to the minus 2, or if you prefer, a over b squared. And 1 is f of 2, because 2, 1 is my other point. So this is a b squared. Okay, so I basically have 2 equations to solve. One of them is 6 is a over b squared. The other one is 1 is a times b squared. So there are many ways to solve this. What you can do when you have like 2 equations, 2 unknown, is try to use one of the equations to solve for one of the variables. We can see that here it's pretty easy to solve for a, like that. And then you replace a by 6b squared in the other one. So that's going to give me 6b squared times b squared. So in other words, 6b to the 4. And solving for b gives me b to the 4 is 1 over 6, right? Just equating this with this and dividing by 6 on both sides. And that means that b is 1/6 to the 1/4. Okay. And then coming back to my initial equation that relates a to b, then a is going to be 6 times 1/6 to the 4th, so that's b squared. So that, what is that? This is 6. So 1/6 to the 4th squared, that's, so the power is going to be 2 over 4. In other words, 1/2. So we have that this is 6 times 1 over 6 to the 1/2, because it's 1 to the 1/2 over 6 to the 1/2, but 1 to the 1/2 is just 1. So we basically get 6 over 6 to the 1/2, and then we can just subtract exponents, so it's 1 minus 1/2, so 1/2. So in other words, which 6 to the 1/2 being square root of 6. So a is square root of 6, and b is, I could write it as 1/6 to the 1/4. I could also write it as 6 to the minus 1/4, because 1/6 is 6 to the minus 1, so both are good. So my model finally is a, maybe I'll write root of 6, b, so maybe for now I'll keep b as this. This is b to the power t, to the power x. X is my variable. So usually we multiply those two together. So this is 1/6 to the x over 4. So I could just evaluate both, by the way. So it's approximately, this is 2.45. This is 0.0639. So a number below 0 to the power x. Okay, so how is that function going to look like? Well, it's going to start at 2.45, and because here my b is less than 1, this is a function that just decreases like this. Okay, so eventually when x is large, it's going to go towards 0, and so the x-axis is an horizontal asymptote as x becomes large.